And welcome to another video in this series of assessments for BTEC. And in this video, like the preceding video, T1, we're going to be making a circuit with a transistor. But unlike in T1, instead of using the transistor as an amplifier, we're going to be using it as a switch, and we're going to be using it in a digital circuit. So the first thing we'll need then is we'll need to understand the difference between digital and analog. And I'm going to get a little portable oscilloscope and some output generators, and we'll have a look at the waveforms. In the preceding video to this one, which was T1, I made a transistor circuit which was a single stage amplifier, and what it did was it took an audio signal in, magnified the audio signal and put it out, and the audio signal is of course an analog signal. This circuit, what I'm going to do is I'm going to make the transistor behave as a switch. I'm going to make it behave as a switch in a digital circuit, and I'm going to use for an embedded microcontroller this thing called an Arduino. I'm also going to enlist the help of this small portable oscilloscope here, and if I zoom into it you'll see that there is a sine wave on it at the moment. And the reason that it's showing a sine wave is that it's hooked in to a small oscillator which is turning DC battery power into an AC waveform. And as you can see, the sine wave goes up, down, up, down, up, down, just like we'd expect from a sine wave. And it's not quite perfect because the two capacitors which are making this work, although nominally the same value, are, due to manufacturing deficiencies, not quite the same value. And that's throwing it off a little bit, but it's not very much, and it's good enough for our purposes that we can see here. Now, an analog output like this is called an analog output because it can be anywhere. Let's say that at the bottom there is 0 volts, and at the crest there we've got 1 volt. And it can be anywhere in between. It can be 0.1, 0.2, 0.3, and so on and so forth. And there's actually an infinite range it could be. And if this oscilloscope was a little finer, we could actually measure it down to infinite ranges. So what I'm going to do is I'm going to detach from the analog. I'm going to put on to the digital circuit with a digital output provided by the Arduino Uno. I'm probably going to have to press a few buttons to see this and change everything round. You'll see the oscilloscope go crazy. Okay, so let's just press a few buttons here, and I'm going to need to alter the time and voltage division so that we can see what's going on. I think that's getting there, to the time and voltage division again, especially the voltage. Now the time, a little bit lesser, still a little bit lesser, and there we can see it. And that is the digital output. I'm going to zoom in on that so we can see a little better what's going on there now. Okay, let's hold that while we see what we've got. So, we've got a direct current. You'll notice that it never dips below this line. And down here is 0 volts, and up here is 5 volts. And that's the difference. You'll notice that it goes very sharply from 0 volts to 5 volts. The digital circuit can't work as an analog circuit. It has 5 volts to play with, and that's it. We can make it by a process of pulse width modulation, switch this 5 volts on and off very, very quickly if we want, to make the receiving device think it's got anywhere between 0 and 5 volts in discrete steps. But at the moment what we're doing is we're switching between 0 and 5 volts, and if we look at the time and space marks Okay, you'll see between these two bars here is the time it's high, and between these two bars here is the time it's low, and that's the same all along the waveform. The time it's low is equal to the time it's high, and both are equal to 1/4 of a second, or 250 milliseconds, which is exactly what we told the Arduino to do in the code. So that's just as we're expecting. Now the fact that it switches between 0 and 5 volts like that is going to be extremely useful when we come to making the transistor a switch, and we'll see why next. In this video we're going to be looking at the transistor as a switch, and in front of us we can see that the transistor here is set up to create a current path to a piezo buzzer. And this is a very simple method around, and it explains how the transistor is going to work. In the preceding video, T1, when we made the transistor an amplifier, we put a signal in through the base. This time there isn't going to be a signal, there's just going to be a pulse. And the pulse will go through the base and cause the NPN transistor to open conduction between the collector and the emitter. I didn't get too mathsy about it last time, but there are some maths behind it. There's maths behind everything if you look far enough. And what we've got here is the current at the collector is equal to the HFE of IB, and a HFE is actually the gain. It stands for something like hybrid parameter forward emitter, or something like that anyway. And usually in a transistor it's around 100, although it can be 200, and in the case of a Darlington it can be as much as 10,000. The current at the emitter is equal to that of the collector plus that of the base. Now usually we can say that the current at the emitter is equal to that of the collector. The current at the base is very, very minimal. We're only going for a few milliamps or even microamps at the base, as the gain can be very, very large. So we can see what happens if the base is activated. Voltage comes down there, goes to ground, and the buzzer makes a loud whaley sound. Let's see it in action. And here you can see the circuit we've just seen simulated made manifest on a breadboard. What we have is the 9 volt supply here, and that goes to the switch. From the other end of the switch we see a resistor of 10k. The resistor goes to the base of the transistor, which is again an NPN. At the collector of the NPN transistor we have a hook to the same 9 volt supply. At the emitter we've hooked the positive end of the buzzer in, and the negative end of the buzzer is hooked here back into the negative end of the supply. So if we press the switch now, and if you are wearing headphones you might want to turn the volume down or move the headphones away from your ear slightly, as this may get loud and raucous. Are you ready? And I'd like to point out where the buzzer actually is. The buzzer is hooked in between the emitter of the transistor and the ground of the supply. And when you do this, this is called an emitter follower. You'll get the same voltage at the emitter, but you'll get a little bit of an increase in the current from the collector due to the current at the base. It's not much, but it helps. This thing takes about 30 milliamps, and that's going to help us work out what to put in there. And of course the question now is, how is this going to help us decide what resistor to put in there? Well, if we look at this load line analysis, what we did when we made the amplifier was we biased it about there, somewhere below the knee. And that gave it the freedom to swing up and swing down without clipping. When we're making a switch, what we want to do is we want to put it so that it's achieved saturation above the knee. What this does is it keeps the switch conservative. It doesn't allow, even if the voltage drops a little bit, for the current to go up and down, which may cause a dropout at the buzzer. Now, let's put a bit of maths in here, because what we know we've got in there is a 10k resistor, and we also know we've got a 9 volt supply, and according to Ohm's law we have 9 over 10,000, and that will give us our current. So the current at the base is 0.009 amps. What's that? 900 microamps. We know that the transistor, in fact, has a gain of 100. So we'll multiply that by 100. And there we are. We're getting 0.09 amps. Now, the buzzer wants 0.03 amps to operate efficiently and properly. So we're giving it 3 times more current than it actually needs. It'll only take as much current as it actually needs, and so the other 2/3 of current there are redundant safeguards, which means that the buzzer will work efficiently and properly regardless of what the voltage, and therefore the current, actually does. So we're keeping the transistor conservative, we're keeping the switch conservative, and in that way we should get no dropouts. When we come to putting the digital system in, we may well need to replace this resistor with something else, because the digital system will only use 5 volts, not 9. I'm going to highlight a small problem with this system. Now what we've got is we've got a transistor. It's an NPN transistor. It will only conduct when there is a pulse at the base. So, if you're wearing your headphones, get ready to move them a bit further from your ears. Are you ready? As soon as I take my finger off the switch, it stops conducting. I'm going to do it again. And as you see, as soon as I take my finger off the switch, it stops conducting. What we'd really like, if this is a proper alarm system, is for it to keep conducting, even if the signal or the pulse at the base is no longer present. And there are a number of ways we can do that. We can either keep the pulse at the base present by using one of these things. And this is a microcontroller board, and you'll find these in most modern digital equipment these days. It's a very, very useful way of getting equipment to multitask, and it's a hybrid of electronic engineering and computer sciences, known as physical computing. However, what we're going to explore before we do that is this thing. I don't know if you can see that there, it's very, very small. It's a curious little thing, and it goes well with this assessment because it is another kind of transistor, and in fact you could call it an extended transistor. It's a thyristor, or a silicon-controlled rectifier, and this is a CP106D, a pretty common one. And what it does is, like a transistor, it starts conducting when it gets a signal at its gate, which is the equivalent of base. But quite unlike a transistor, it keeps conducting if that signal has disappeared. So I'm going to put this into the circuit and we'll see what we can do. So before we go sticking the thyristor into a practical circuit, it's probably best to see what the theory behind it is. Now, previously I said that a thyristor is an extension of a transistor, and what we're looking at in front of us here is a model of how the thing is constructed. So this is the basic thyristor, and as you can see it's got 4 layers, P, N, P, N. Now from what we've done here and what we did in the previous video, the NPN side should be very familiar. That's just a transistor. The PNP side may not be so familiar, but it's another kind of transistor. We haven't actually looked at PNPs yet, but we're going to do that in the next video. So basically what we've got is a PNP there and an NPN there, 2 transistors mashed together. Now then, that's what it is. Let's go into how it works, and a full explanation of how it works would go into chemistries and substrates, and at one point, if we went deep enough, we'd also be in the realm of quantum physics, and we really don't want to do that because our interest here is in getting the thing working and not in the physics meat and two veg of how it actually does it. So what follows is a very simplified explanation, but it's still a little confusing, and I'll go quite slowly because, frankly, I may well confuse myself if I go fast on this. So, are we ready? Let's begin. The P substrate of junction 2 here acts simultaneously as the base for the NPN and the collector for the PNP. Applying a voltage means the NPN can conduct. The base of the PNP is simultaneously the collector of the NPN. As the NPN conducts, the base of the PNP finds a ground path, which means that conduction from the emitter to the collector of the PNP can occur. As we know, the PNP collector and the NPN base are the same substrate. And so the base will get from the PNP a continuing pulse even after the initial pulse at the gate has absented itself. What all this means in plain English is that the thyristor actually latches on. It won't stop conducting after the initial pulse has been applied. In this way, it's the semiconductor equivalent of a relay. So, when we get to the practical circuit, you'll see what the advantage of this is. This is what the practical circuit is going to look like, and as you can see we've got a voltage here, and it's tied directly to the collector of the NPN transistor. And the NPN transistor is driven from the base via a 330 ohm resistor, and at the emitter we have the piezo buzzer, which goes to ground, and that doesn't look too different from what we had before. What we have added in is the thyristor here. The anode is applied directly to the voltage rail, and the cathode goes into that 330 ohm resistor to drive the base of our NPN transistor. It doesn't take much to set the thyristor off. What we've got here is a 22k resistor. We only need very, very small amounts of current in at the gate. Because we only need very, very small amounts of current in at the gate, any random fluctuations in the air, such as from a nearby radio, could set the thyristor off. And to combat that, we have a 10 microfarad capacitor to shunt away any AC fluctuations. So let's get that on breadboard and see what we've got. And what we have here is the circuit that we saw on the simulator made manifest on breadboard, and if we zoom in a little bit we can see the parts that we've added. So, most importantly is a CP106D thyristor, which is this little black device here, and from the switch there's now a 22k resistor which is put there so as not to give the thyristor too much of a shock, and that goes to the gate of the thyristor. The anode of the thyristor has been hooked directly into the 9-volt rail, and coming from the cathode we have a 330 ohm resistor going to the base of the NPN transistor. Let's zoom back a little bit and we can see a capacitor, and that capacitor is supposed to be there to shunt away AC transients. And as I was building this circuit it occurred to me that may well be in the wrong place, because what it could do there is it could charge, and it would be charging very slowly through this resistor, and it could rob current from the buzzer here. Well, I'm going to press the button and we'll see what happens. Now, as I press this button, what I'm hoping is that, unlike last time when the circuit stopped buzzing when I took my finger off the button, the thyristor will cause it to latch on and keep buzzing regardless of whether my finger is on or off this button. So, once again, if you're wearing headphones, now might be a good time to put the volume down or remove the headphones a bit further away from your ears. And if you're ready, here we go. Well, that certainly works, and just to make sure it works a second time I'm going to press the button again, and if you're ready, on reflection it looks as though my fears about the capacitor were a bit groundless, but I'm still going to move it back, and I'm going to move it back there before the 22k resistor rather. Press the button again and see what happens. Are you ready? And the capacitor retains a bit of charge there, so that's not too bad. We'll leave the capacitor where it is. It should get rid of any transients before it shoots down that resistor and gets to the thyristor. Might have a bit of a problem there, so I'm going to put something else in there to combat it that end. And what I'm going to do is I'm going to put a low value resistor in here, and from that low value resistor I'm going to run an LED, and hopefully what I should get is a light on the alarm as well as a buzzing. Let's see. If you're ready to remove your headphones, I'm going to press the button 1, 2, 3. Well, that seems to work. Now, as an electronic project, that's looking fairly simple, yet nice circuit. And if this was an electronic project, then we could leave it like that, because what we've made here is the prototype for something like a personal attack alarm, and that would be very, very good. However, we're not doing this course in electronics, we're doing this course in IT, hardware and support. So really it behoves us to use some sort of mini computer or microcontroller to do the job of this switch. And if we do that, we can get rid of the capacitor and a couple of the resistors and the thyristor and just leave the LED and the buzzer and the transistor in there. And the advantage of that is ease of expansion. We can put more switches on the microcontroller with no fuss or hassle than we can on to a discretely made circuit like this. So we're going in the next section of this video to use, if I can get it out of the box, Arduino and one of these chaps, which is an SR04 proximity sensor. And what we're going to do is we're going to make a proximity alarm with this circuit and those other two components we've just seen. This is the point where the project's getting truly digital now. It's been digital so far only in the sense that it's been binary. Either there's a pulse at the base or there isn't. And what I've got in front of me here is a wiring diagram of what I intend to do next. And as you can see, this is the circuit we've already seen, the NPN transistor and the mechanical buzzer and the LED from the last section of the video. We've got rid of the capacitor and we've got rid of the thyristor because what's going to do that job is this thing up here. And this is a digital microcontroller. It's an Arduino Uno. You can get smaller Arduinos, the Zero, the Pro Mini and so on, which take up less footprint. And the Arduino is a popular microcontroller board with makers, enthusiasts, hobbyists and people who do small scale production runs, because it's very cheap and very easy to work. And it's also very, very reliable. You're getting a professional grade microcontroller board for what, about £15–16, and what it does is, where there's a big black square here on the real board, there's an actual Atmega 328p, and this black square here is a USB to serial converter. So basically you're getting a microcontroller that you can program via an IDE very, very easily to do what you want. And what it does is it reacts to a series of inputs and does the appropriate output. And the input we're doing here is a module. And this is it. It's an HCSR04. And what that does is it shoots out blasts of ultrasound and looks for them coming back. When it comes back, we can time it with the Arduino Uno, and what we can do from the time it takes to come back is calculate the distance. And if the distance is a proximity that we set, then we can tell the Arduino Uno to send a pulse to the NPN transistor, which will make it conduct and make the piezo buzzer sound and the LED light up. Well, there's the theory. So let's see what happens in practice. Well, there is an old saying that the proof of the pudding is in the eating, and the pudding we're going to eat here consists of this. It's an Arduino Uno attached to a circuit and attached to the SR04. So let's zoom in a little bit on it and direct the camera to it, and we'll see what we've got. Well, we have the remnants of our old circuit here. I'll zoom in on that a little bit if we can. Bear with me. I'm not sure this is going to resolve fine enough. Let's try this. That's better. And as you can see, what we've got left is the transistor that we've had all along, and which is of course the subject of this discourse, and a 300 ohm resistor there at the base. We've got an LED as we had before, and we've got a 560 ohm resistor driving that, and of course our buzzer here as the emitter follower. I'll zoom out a little bit more now. We have the Arduino attached to the base of the transistor, and at the other end, pin 7 of the Arduino is attached to this wire here. Something I didn't show on the drawing, but which the Arduino really needs if it's to work with this circuit, is a common grounding. So there is a common ground between the Arduino and the breadboard there. So what we've in fact built here is a proximity alarm, and you often see these things in visitor centres. And what happens is, as the visitor goes 5 or 6 inches towards the exhibit they want you to look at, the sensor will kick in and it will activate a sound and light show. So here's a visitor, and he's walking up to the SR04 slowly, as visitors tend to do. And as he gets a bit nearer, I'll do that again. There we go. Works in quite a wide angle. And you'll only do that if the visitor is so many inches away. Here's my hand. Now, we may have gone very high-tech here, using a microcontroller, but the microcontroller can only do so much on its own. It's a physical computing device, and it needs other devices attached to it to actually do any useful work. And here, as it's always been throughout this video, it's this thing that's doing the actual job, the transistor. Zoom out, and let's recap on what we've been doing so far. So we've looked at the thyristor, and we've looked almost exclusively, in fact totally exclusively, at the NPN transistor at the moment. And what we found is that if we don't disable the alarm, it'll go off again. What we found is this. We've used it as an amplifier, and we biased it above the cutoff point but below the knee, somewhere in the mid-range there. And we put in a waveform that undulates like that. And we've got out the same waveform but much larger, amplified. And when we've used it as a switch, as we did with the alarm just then, we've had it at cutoff. We've had no current or voltage through there whatsoever. And when we do switch a current and voltage on, we bias it above the knee. And that makes it very, very conservative, and we end up with a waveform that looks like that. The top one is analog, and the bottom one is digital. Now with that, we can conclude this video, and we can go on to the next one. And in the next one I intend to look at PNP transistors, which we've neglected quite a lot so far. And it's going to be quite a short one, because I'm going to do the difference between the operation of PNP and NPN.